Assalamu alaikum. Welcome to the Chemistry Subject Knowledge Day 2 training. I hope you're ready to join us for another day of Foundations in Chemistry and reviewing the Cycle 3 chemistry topics. So, let's go through the ground rules again. Let's try to stay on target, work well with each other, make sure we don't use our mobile phones, and I'll do my best to stay on time. Of course, if you're joining us online, you can use the message box to ask any questions that you might wish to whilst we go through the training today. So today's agenda, I'll go through the aims and objectives of the training, and then we're going to look at classification of hydrocarbons, alcohols and alkyl halides, ethers and amines, aromatic and carbonyl compounds, and then we'll review the day. So, let's get started. So the aim of today's training is to review the Cycle 3 chemistry concepts that you teach in your curricula. At the end of this training, all learners will be able to distinguish between functional groups of organic compounds, determine the IUPAC names for various organic compounds, differentiate between types of functional groups, review the preparation of some organic compounds, and clarify the products of chemical reactions of organic compounds. So let's start with a quick review of hydrocarbons. Let's see if you can refresh your memories and think about how we draw the structures of different atom arrangements for some hydrocarbons that we know. So I'd like you to use the whiteboards with us online, or you can use a piece of paper, draw and share the pictures with us if you're here with us today. Now, A, we want to look at 6 C atoms, no multiple bonds and no rings. B, 4 carbon atoms, 1 double bond and no rings. And C, 4 carbon atoms, no multiple bonds and 1 ring. So off you go. You've got 10 minutes to complete this task. Okay, that's your 10 minutes up. Now, let's have a look at the solutions. Let's see how well you refreshed your memories. So, solutions for A, 6 carbon atoms, no multiple bonds and no rings. So that you can see that we've got both a 6 carbon straight chain, then we've got a 5 carbon chain with a 1 carbon methyl branch. We've got a 5 carbon chain with a branch on a different central carbon atom. We've got a 4 carbon chain, 2 options there with branches on different carbon numbers in the straight chain. Well done to those of you who were able to come up with those solutions. Let's have a look at solution B. 4 carbon atoms, 1 double bond and no rings. So you can see we've got 2 options for the 4 carbon chains. Those of you that can remember isomers will understand why. We've only got 1 option for the double bond branching from carbon number 3 to 4. And we'll look at isomers a little bit later on, as I said in the agenda. And then we also have the 3 carbon chain with a double bond. Well done. Let's have a look at solutions for C. So 4 carbon atoms, no multiple bonds, and 1 ring. So you can see the 2 different types of carbon rings that we've got there, one with 3 carbons and one with 4. Well done, that was a great starter to the day. And those of you with me today, I think everybody got those right. Well done. Okay, so let's go straight into the training now after that little refresher with hydrocarbons. What are we going to look at? Alkanes. So, refresher. Methane, ethane and propane. Methane, we have 1 carbon, ethane 2 carbons, and propane with 3 carbons. Alkanes are hydrocarbons that contain only carbon and hydrogen. Alkanes are hydrocarbons that contain one single bond and are referred to as saturated hydrocarbons. The general formula for an alkane is CnH2n plus 2, where N is any positive integer. Alkanes comprise a homologous series, a group of compounds in which each member differs from the next by a CH2 group. With alkanes, the name of an organic compound is comprised of three portions: prefix, the root, and the suffix. The root name of the compound is determined from the number of carbon atoms in the longest continuous chain. The suffix indicates the type of organic compound and is placed after the root. The suffix for an alkane is -ane. The prefix identifies any groups that might be attached to the main chain. Okay, so let's have a look at the numerical roots for carbon chains and branches. This is something that we often work with our students in terms of learning the molecular formulas and the names that go alongside them. So, of course, one carbon is methane. Two carbons, ethane. Three carbons, propane. Four carbons, butane. Five carbons, pentane. Six carbons, hexane. Seven carbons, heptane. 8 carbons, octane. 9 carbons, nonane. And 10 carbons, decane. So, of course, you all know that when it comes to chemical compounds, and today we're starting with alkanes and the organic compounds, we have rules for naming, nomenclature, which again we'll look at further in detail. And you'll find these rules in your resource pack attached with the course in the learner guide. The main areas that we need to remind ourselves of are points 1, 2, and 3. And again, this is in your learner guide. And of course, you can very easily find it online from companies like McGraw-Hill. So, rule number 1, naming the longest chain, the root. The rule is always to find the longest continuous chain of carbon atoms. So the example you can see there is 6 carbons, which gives us hex. Then, second rule, naming the compound type, the suffix. So for alkanes, we already said that the suffix is -ane. And in this example, that means we will have hexane. Don't forget that if you find a chain which forms a ring, the name would be preceded by cyclo, for instance, cyclohexane. And then rule number 3, naming the branches. So remember, the branches are the prefixes. So each branch name consists of a subroot, which is the number of carbon atoms, and the ending "-ile" to signify that it is not part of the main chain. So you can see here, as we said in step 1, we've got hexane, ane found in step 2. And when we look at the molecule in question, we have an methyl group and an ethyl group. So when we have 2 or more branches, their names will always appear in alphabetical order. That means the name of this compound so far is ethyl methyl hexane. But if we look at part C, we can see that we have not stated where the ethyl and methyl groups can be found. So to specify where that branch or group occurs along the chain, we start at the end closer to a branch to achieve the lowest numbers for the branches. So in this case, we have 3-ethyl, 2-methyl hexane. So once we've gone through the rules for nomenclature and naming, we look at the ways of depicting the alkane. It's the same alkane that we used in the previous slide, and now you can have a look at different ways of depicting, showing the actual molecule. So we have the expanded formula. We could also have the condensed formula, which is what we used in the slide previously. And then we've got the carbon skeleton formula, one which most students find a little bit difficult. But then, of course, we have the ball and stick models, which we use in our classrooms and help students with their learning very often because they are able to visualize the branches and the chains. And then we have the space filling model, which shows us the interactions of different atoms within a specific molecule. And we very often use that to simulate online reactions or interactions between molecules. And just as an added extra, you can see that there's different ways to depict the cycloalkane. So remember we said that we must always put the prefix cyclo when we have the carbon atoms bonded in a cycle. So you've got 2 examples there and 3 different ways of depicting those 2 molecules, cyclopropane and cyclobutane. 2 more examples here for you, cyclopentane and cyclohexane. Okay, so that's ways of depicting our alkanes, both straight chain and cycloalkanes. Now let's move on to the concept of constitutional isomers. Constitutional isomers. They are constitutional or structural isomers that have the same molecular formula, but a different arrangement of the bonded atoms. So here you can see that we've got a molecular formula of C2H6O. And you can see 2 possible structures, ethanol and dimethyl ether. Same molecular formula, 2 different possible structures, a constitutional isomer. A straight chain alkane may have many branch structural isomers, and it's a good practice to go through these with your students at Cycle 3. Structural isomers are different compounds and have different properties. If the isomers contain the same functional groups, however, the properties will be similar, an important point to remember. So, let's have a look and see how you do with this task. We've got alkanes, constitutional isomers of C4H10 and C5H12. You've been given the systematic names there, and I want you to take, let's say, just 10 minutes to see if you can come up with the expanded formula. So remember, in the expanded formula, you're going to show all bonds and all atoms. Take 10 minutes now and see if you can come up with the answers for the expanded formula of the constitutional isomers of C4H10 and C5H12. Okay, let's see how you did. Let's start with butane. You can see butane, 2-methylpropane, also known as isobutane. We have the expanded formula. Butane is a straight chain, whilst 2-methylpropane has a methyl group attached to carbon number 2 in the straight chain. You can also see the examples there of the condensed and skeleton formulas. Now, pentane, nice and easy. Pent is 5, so pentane, we've got a straight chain in the expanded formula. With 2-methylbutane, again, the methyl functional group is on carbon number 2. Also, you've got the condensed and skeleton formulas there for your perusal. What about 2,2-dimethylpropane, also known as Neopentane? Let's see who got this one correct. So, dimethylpropane, 2,2. The clue was in the 2 and the 2. That means both the methyl, because we had dimethyl meaning 2, both methyl groups are found on carbon number 2. And there you can see the condensed and skeleton formulas as well. Well done. Okay, well done. That was some good revision on alkanes and constitutional isomers. Let's see where we're going next. So what I'd like you to do now is we're going to do a quick quiz together. I'll share the screen with you so you're able to find where the Chem Quiz is available online for everyone to use. Okay, so let's have a go, team. What's the name of this molecule? CH4. Let's have a go. Methane, correct. Well done. Next question. I'll give you a moment to work it out. We can go through the options, and of course, if you're playing this later, you can easily take the web address and have a go. It's also a very good tool to use in your classrooms. Oh, I can hear some answers from the people with us today. Pentane or propane? Which one are you going to go for? Pentane? Let's have a go. Well done. Excellent. 2,2-dimethylpentane. Very good. One of the examples we had in our presentation. Okay, so we've got a cyclical molecule here. Let's have a look if we can find any of the names. Oh, I've got 2 possible answers for you, hexane or pentane. Okay, the team are saying hexane. Let's go. Nope. 5 is pent. Remember your naming rules. Next question. Remember the naming rules here that we went through earlier? I'll scroll through the possible answers. Pentane, you say? Correct. Well done. Okay, what do we have here? Let's count the number of carbon atoms in the straight chain. 3. And how many functional groups? 1. Any answers that you want to pick there? You think it's 3-methylpentane? Or you think it's 2-methylpropane? Well done. Excellent. Okay, another cyclical molecule. what do we have here? Let's count the number of carbons in the cycle. And then once you've counted them, are there any functional groups? What are you going for? Butane? Are you sure? Hexane? Butane? Can't be hexane. Can't be butane because it's cyclical. So, you want to go for cyclohexane? Correct. Well done. Okay, another straight chain. You're saying 2-methylbutane. Are you sure? Let's have a look. Well done. Excellent. Straight chain again. No branches. Let's look for the answers. You think it's butane? Well done. Looks like this revision was working. So now we've got a straight chain, 5 carbons long, 2 functional groups. Got it wrong this time. Let's look carefully why we got it wrong. The number of carbons in the straight chain is 1, 2, 3, 4, 5, and we chose bute, which is 4, and the correct number is 5, and that's pent. Let's go for another question. We've got a branch coming off the central carbon atom. I'm not going to help you on this one. I can hear some answers coming through. Those people live with us today. Methylpentane. No, it wasn't. It's 2,2-dimethylpropane. We've got a straight chain going all the way down. This is carbon number 2. So carbon number 2 has 2 functional groups attached to it. Next question. Straight chain. Count the number of carbons. 5. What do you think the answer is? Well done. Okay, so we'll stop the quiz there for now, but that's a fantastic tool to use very easily when you're teaching online or to revise yourselves and to share with your students. Okay, so let's move on now to our next organic compound, alkenes. What do we know about alkenes? And what can we remember about alkenes? Let's have a look. So alkenes are hydrocarbons that contain, that's right, you remembered well, at least one carbon double bond. 2 examples there, ethene and propene. Alkenes are said to be unsaturated and have the general formula CnH2n. To name an alkene, the root name is determined by the number of carbon atoms in the longest chain that also contain the double bond, an important rule to remember. The carbon chain is numbered from the end closest to the double bond. And the suffix for alkenes is always -ene. So now let's have a look at some geometric isomers, which quite often occur in alkenes because of transition around that carbon double bond. So the double bond of an alkene restricts the rotation so that the relative positions of the atoms attached to the double bond are fixed. Alkenes can exist as geometric cis or trans isomers, a good piece of revision there for you, which differ in the orientation of the groups attached to the bond. Geometric isomers have different physical properties. So, here's an example, again from McGraw-Hill, of some geometric isomers. Cis-2-butene and trans-2-butene. Let's move on now to alkynes. An alkyne is a hydrocarbon that contains at least one carbon triple bond. There you have an example. Not named it for you. Let's see if you can name it. Alkynes have the general formula CnH2n2, and they're also considered unsaturated carbons, just like alkenes. Alkynes are named in the same way as alkenes, using the suffix "ene", but it's spelt with a Y-N-E. So, let's do a quick activity now. You have 5 different compounds there. You've got your learner guide with the rules for naming organic compounds in there. And what I would like you to do, as per the instructions, is give the systematic name for each of the following. And for D, indicate what the chiral center is. And draw 2 geometric isomers for part E. So off you go. You've got 25 minutes to complete that task. Do use the learner guide to remind yourselves of the rules for this task and activity. And I'll get back to you in 25 minutes. Those of you that are online, you can ask me any questions in the chat box. And I'm right here to answer your questions. Okay, so that's your 25 minutes up. Let's start going through the answers for solution A. So what do we have here? 2,3-dimethyl butane. So you can see that we've got 2 methyl groups and they are both on carbon number 2. So can you tell me if that name that you see there is correct? 2,3-dimethyl butane. No, because both of the methyl groups are actually on carbon number 2. So the correct name is, let me hear it. Yes, that's correct. 2,2-dimethyl butane. Well done. Excellent work there. If you annotate the answers that you came up with in case you've got any corrections to make as we go along. Okay, so now what do we have? We have hexane. We have a methyl group on carbon number 3 and carbon number 4. So the name of this molecule is 3,4-dimethyl-hexane. Excellent. Well done to those of you that got it right. You can see how the numbering goes, and remember the rules to start with the lowest number. It means that the functional group closest to the beginning. That's why we get a 3, 4. Well done. Okay, so we had a cyclical compound here, and we have an ethyl group, and we have a methyl group. So we have 1 ethyl, 2 methyl cyclopentane. Remember that we keep the naming for the groups to be on the lowest carbon number, and that's why we wouldn't call it 4 methyl, 5 ethyl, because then the group number would not be according to the nomenclature rules that you find in your learner guide. Excellent, well done. Okay, so what do we have here? We have a pentene, yes, because that's right, the carbon double bond is there. We have a chiral center, 2 carbons on either side. And then we have a methyl group on carbon number 3. The double bond is between carbon number 1 and 2, so we get 3-methyl 1-pentene. Excellent, well done. Now let's have a look at our geometric isomers for solutions for E. So here we have a cis isomer with 2 methyl groups, and yep, it's a alkene, so it's hexene. So we have cis 2,3 dimethyl 3, carbon double bond is at the 3, hexene. Well done. Now what about the other isomer? What do we have there? Trans. So you can see we now have trans 2,3 dimethyl 3 hexene. So we still have the carbon double bond in the same place. However, the functional groups are on opposite sides, so we have a trans isomer. Fantastic, well done. Take a moment to have a look at those answers and annotate any of your diagrams and answers that you did. Well done. Okay, so now we've done those worked examples, let's start thinking about the types of reactions that we see with organic compounds. The first one that we're going to start with is addition reactions. Can any of you remind yourselves, take a minute to think about what an addition reaction would be, or any of those that are taught at Cycle 3? And remember, we're talking about unsaturated reactants becoming saturated when they produce a product. Let's have a look at an example. So you can see that we have an unsaturated alkene going through a reaction to become saturated. That means no double bonds. Addition reactions. So we're adding functional groups to our molecule. The carbon double bond, the carbon triple bond, and the carbon oxygen double bond commonly undergo addition reactions. So they are good to remember in your revision of Cycle 3 chemistry. In each case, it is the double bond or the triple bond that breaks, leaving the chain intact. So let's have a look at some addition reactions that we focus on in Cycle 3 chemistry. So we started with an alkene with the addition of hydrogen chloride. And what you see there is the double bond is broken, and we have hydrogen and chlorine added to our molecule. You can see the reactants and the bonds broken and the products in the bonds formed. Nice and simple addition reaction as a reminder for you there. So what does this look like in the classroom in Cycle 3? What kinds of experiments can we do at Cycle 3? Well, we have bromine can react with an alkene, and what we see is the orange-brown colour of bromine disappearing. We get to a point where there are no carbon double bonds left, so the orange-brown colour of the bromine does not disappear because it has no further reactant molecules to react with. And there you can see what's happening in terms of bond formation. Okay, so that was the first type of reaction that we were looking at. Can anyone think of or remember the other two types of reactions that we might explore at cycle 3 chemistry level? Let's take a look, shall we? Elimination reactions, you got that right. So, addition reactions, we added some functional groups. What's happening with the elimination reactions? Elimination reactions occur when a saturated reactant becomes an unsaturated product. It is actually the reverse of addition. So you recall in the previous slide, we added the X and Y functional groups. And now, in an elimination reaction, we are removing them. The groups typically eliminated are hydrogen and a halogen atom, or hydrogen and a hydroxyl group. So, elimination reactions in a little bit more detail. The driving force for an elimination reaction is the formation of a small but stable molecule, such as hydrogen, chloride, or water. As you can see here, addition of H2SO4 gives us the product of water being formed. Same reaction, different depiction using the stick and ball. Remember that very often getting students, when they can't do experiments in the classroom, to actually use the ball and stick to understand what's going on, help make the reaction seem real, especially when you're looking on a molecular basis like this, and especially when we're looking at addition elimination. And I'm not going to say the name of the next one. Let's see what the other type of reactions are that occur. That's right, you got it. Substitution. So we've got elimination, addition, and substitution. What happens in substitution reactions? Let's have a look. So a substitution reaction occurs when an atom or group from an added reagent substitutes for one attached to a carbon in the organic reagent. So it's exactly what it says. There, a substitution takes place. So previously we had an elimination and an addition, and now we have a substitution. The carbon atom at which the substitution may be saturated or unsaturated, and X and Y can be many different atoms. So substitution reactions in a little more detail. An example. Main flavor ingredient in banana oil is formed through a substitution reaction. Look at that. Again, ball and stick makes a very good use of applying knowledge in the classroom for cycle 3 students. So, an activity for you. We'll take 15 to 20 minutes to do this one. And what you need to do is take each example A, B, and C and state whether each reaction is an addition, elimination, or substitution. I'll give you 15 to 20 minutes to do this. Make sure you have a look at it in detail and use the rules shown to you on the previous slides to make your decisions. We'll be back with you in about 15 minutes for 5 minutes of feedback. Okay, great. Some good questions asked there. Shall we go straight through now to the solutions? Let's have a look. Where do we find ourselves? So, A, it is in fact an elimination reaction. If you look very carefully at the starting molecule, you have a functional group of bromine attached, and at the end of the reaction, you have hydrogen bromide produced. So, 2 bonds in the reactant, the carbon hydrogen and the carbon bromine, are absent in the product. Excellent. B started with a cyclical compound. So you can see a cyclical compound that had a double bond where hydrogen was added. So now 2 more carbon-hydrogen bonds have formed in the product. Nice and simple, an addition reaction. And then C. So we had a carbon double bonded oxygen. And what was substituted? It can be a little confusing because the product still showed the carbon double oxygen bond, but you can see that we actually substituted bromine from the reactant molecule by a carbon oxygen single bond in the product. Well done. Well done for getting those reactions right. Addition, substitution, and elimination are good reactions for you to explore in your Cycle 3 chemistry classrooms and for you to revise your own personal chemistry as well. It's always good to go through the learner guide and have a look at any reactions that you might find there and make sure you feel familiar with them all. Okay, so you've been going well for a good almost 2 hours now with your activities and the working out of the solutions and going through the learner guide. I think it's time for a quick coffee break. We'll meet you back in, let's say, 15 minutes. Okay, guys, see you in 15. Welcome back after the break. So we have a short video for all of you. Pay attention. Let's see what they've got to tell us.
Hello everyone. In our previous lesson, we learnt about OH functional group, which is found in all alcohols. Now, there are few other common groups. For example, aldehyde group. If you see the structure here, it has the group CHO. So you can say aldehyde is a functional group which consists of a carbon atom that is bonded to a hydrogen atom and double bonded to an oxygen atom. And all the compounds having this group have the same common properties. For the organic compounds having this group, that is aldehyde group, the name ends with Al. Thus we see here ethanol, which means it has 2 carbon atoms because the name ethanol starts with eth and the suffix al indicates the presence of CHO group. So here 1 carbon atom comes with aldehyde group. And this is propanol. Why? 3 carbon atom means prop is the prefix and al is the suffix because of aldehyde group. Another common group is ketone, which has a carbon atom bonded with an oxygen atom with a double bond. You know, the double bond between carbon and oxygen is known as the carbonyl group. You know, compounds having ketone group have ONE as the suffix. For example, propanone. It has 3 carbon atoms, one of which comes with ketone group. That is a carbon atom bonded with oxygen with a double bond. Another very well-known group is carboxylic acid group. The general formula for it is COOH. The vinegar we use is one such compound. Any organic compound having this group behaves like an acid and it has name that ends with OIC acid. Like here we see ethanoic acid, which has 2 carbon atoms because of the prefix eth, and one of the carbon atoms has carboxylic acid group. And here we see the structure of propanoic acid, which has 3 carbon atoms and one of the carbon atom has carboxylic acid group. Now We have seen that all alkanes, that is the saturated hydrocarbons, have the same general formula, that is CnH2n plus 2. And also all alkenes have the same general formula, which is CnH2n. Same way, all alcohols have the same general formula, which is CnH2n plus 1 OH. And thus we see the formula for methanol is CH3OH. For ethanol, it is C2H5OH. And for propanol, it is C3H7OH. So remember, the general formula for all alcohols is CnH2n plus 1 OH. You know, a series of compound which has the same general formula is called a homologous series. So we can say alkanes are example of homologous series as they have the same general formula CnH2n plus 2. And also alkenes are example of homologous series as all alkenes have the same general formula CnH2n. So that was all for today. Bye-bye.
Okay, so that was an excellent video with a quick reminder of functional groups. So we know it features very widely in the Cycle 3 organic chemistry curriculum. Let's think about functional groups that we come across. Alkanes, alkenes, alkynes, cyclical benzene rings, another functional group, amines, alcohols, ethers, alkyl halides, and so on and so forth. So what about these functional groups? Organic compounds are classified according to their functional groups. A group of atoms bonded in a particular way. That's a functional group. The functional group in a compound determines both its physical properties and its chemical properties and its chemical reactivity. Functional groups affect the polarity of a compound and therefore determine the intermolecular forces it exhibits. And functional groups define the regions of high and low electron density in a compound, thus determining reactivity. So you can see that functional groups are very, very important in both physical and chemical properties and reactivity, as well as helping us to name and classify the chemical compounds that we come across. So, important functional groups in our organic cycle 3 chemistry. Alkenes, alkynes, alcohols, haloalkanes, amines, aldehydes. You've got many different functional groups that our students come across in cycle 3 chemistry. And how can we help them with this? Let's start by looking at alcohols, shall we? So, the alcohol functional group consists of a carbon bonded to a hydroxyl or OH group. Alcohols are named by replacing the E at the end of the parent hydrocarbon name with the suffix -ol. Alcohols have a high melting point and boiling point since they can form hydrogen bonds between their molecules. So let's think about nomenclature now. Can you name the alkyl group associated with the hydroxyl group, then followed by the word alcohol? So let's have a look. Example 1, CH3, CH2OH. That's right, ethyl alcohol. Then we've got a carbon double bond, so we get a vinyl alcohol. We've got 3 carbon chain with a hydroxyl group next, an allyl alcohol. And if you look below, we can see the nomenclature and the naming function for propyl alcohol, butyl alcohol, and sec-butyl alcohol. So, IUPAC nomenclature. Let's have a look at a quick video.
You can review content from Crash Course Organic Chemistry with the Crash Course app, available now for Android and iOS devices.
Hi, I'm Deboki Chakravarti, and welcome to Crash Course Organic Chemistry. Even when we speak the same language, we have different ways to say the same thing. Do you call a carbonated beverage a pop, soda, or just Coke? Or maybe you're looking for a drinking fountain and everyone keeps pointing you to a bubbler? Other times we're not saying what we think we mean. For example, an American asking for chips in the UK isn't going to get a bag of crispy potato circles. If they shout out for their friend Ken in Japan, people might wonder why they're yelling about a sword. Or if they're trying to say they're embarrassed in Peru with a fragmented I'm embarazada, they're actually saying they're pregnant. Language is complicated, and it can be especially confusing in the chemistry lab. If we ask our lab partner to pass the dichloromethane and they hand us a bottle labeled methylene chloride, is that the same chemical or not? To unite the scientific community, the International Union of Pure and Applied Chemistry, otherwise known as IUPAC, was established in 1919. This group wanted to make sure that chemists around the world could communicate accurately. 100 years later, IUPAC is still the guiding organization for all things nomenclature. Thanks to them, we have some standard rules for naming organic chemicals. By the time IUPAC came along with standard rules, organic chemistry as a field was already over 100 years old. Many chemicals had common names given to them by the people who discovered them based on their source or smell or color. For instance, vanillin is isolated from vanilla beans, and cinnamaldehyde is isolated from cinnamon. Alcohol, ether, acetone, and acetic acid are common names too. While some common names might sound fun, you have to memorize them. And they don't tell you much besides, like, there's a chemical responsible for the flavor in vanilla ice cream called vanillin. Not super useful for learning chemical structures. Sometimes chemists even disagreed about what each common name meant, sort of like regional differences about what to call a carbonated beverage. Despite IUPAC's best attempts to make organic chemistry nomenclature less confusing, many common names are still used today. Probably because vanillin is easier to say and put on a bottle than 4-hydroxy-3-methoxybenzaldehyde. But that longer name is a systematic name that follows a set of rules, which means anyone who knows those rules can draw the structure. There are 3 basic steps to IUPAC systematic naming. We'll add more as we discover more about organic molecules throughout the series, but for now, these will get us started. Number 1, find the longest carbon chain and give it a root name. Number 2, identify the highest priority functional group and add its suffix to the root name. And number 3, identify the types of substituents and their positions on the carbon chain. Then add a numbered prefix to the root name. So we start building any systematic name with the root name, which comes from the longest carbon chain in the molecule. The word longest is key because some molecules will have long chains sticking out that can throw you off. So make sure to do a little extra counting to make sure you actually found the longest one. Carbon chains containing up to 4 atoms have arbitrary sounding root names. 1 carbon is meth, 2 is eth, 3 is prop, and 4 bute. This can be a little tricky to remember, but you can use this mnemonic to help. Monkeys eat purple bananas. For carbon chains with 5 to 12 atoms, the root names are similar to geometric shapes. For example, a pentagon in geometry is a 5-sided ring. And if a carbon compound has the word pent as its root, then it's a 5-carbon chain. A 6-carbon chain is hex, 7 is hept, 8 is oct, 9 is non, 10 is dec, 11 is undec, and 12 is dodec. If you need a root name for a carbon chain with more than 12 atoms, I don't have it memorized. There are plenty of resources out there to look them up. Chemists usually don't deal with longer chains, and there are plenty of other things to remember besides what a 56 carbon chain is called. Back to our IUPAC rules. Once we've counted our carbons and have a root name, we need to add a suffix to indicate what kind of organic molecule we're dealing with. The simplest organic molecules are hydrocarbons, which only have hydrogen and carbon atoms. There are 4 kinds of hydrocarbons: alkanes, alkenes, alkynes, and aromatics. But we'll only talk about the first 3 for now, because smelly aromatic compounds are a little more complicated. Alkanes only have single bonds between carbons. For these compounds, we take the root name and tack on a suffix ane. For example, this skeletal structure is a 6-carbon chain, so the root is hex. And because there are only single bonds, it's an alkane, and we add the suffix ane. It's hexane. Alkanes are kind of boring compared to their hydrocarbon cousins. They're low-energy couch potatoes and don't interact with many other compounds. On the other hand, alkenes and alkynes have functional groups. Remember last episode we said that functional groups are where all the cool chemistry happens. In alkenes, the functional groups are double bonds between carbons. And in alkynes, the functional groups are triple bonds between carbons. Alkenes and alkynes can do fun reactions to make things like light-emitting polymers, which are big molecules with regions where electrons kind of move around on a racetrack that absorbs energy and emits light. But I'm getting ahead of myself. To name an alkene, we find the longest chain of carbon atoms, and it must include a double bond. If the longest carbon chain doesn't include a double bond, it's not named as an alkene. Sorry, I don't make the rules, IUPAC does. Since IUPAC rules are all about communication, we want to let people know where that double bond is on the chain. So we'll number the carbons starting on the end closest to the double bond. For the sake of consistency, we want to keep the numbers as low as possible. Then we'll take the lowest number touching the double bond, combine it with the suffix ene, and add that to the root name of our chain. For example, the longest chain in this molecule is a 5-carbon chain, so the root is pent. Because there's a double bond, we know the suffix is ene, but we also have to number the carbons. Starting from the end closest to the double bond, that's 1, 2, 3, 4, 5. And because the double bond is between carbons 1 and 2, this compound is pent-1-ene. Notice the punctuation here. We stick dashes around the number. To name alkynes, the hydrocarbons with a triple bond, we do the same thing. First, we find the longest chain of carbon atoms and pick a root name. Then we number the chain from the end closest to the triple bond to let people know where it is, and tack on the suffix -ine. For example, an 8-carbon chain with the triple bond in the center would be called oct4-ine. To finish the IUPAC rules, once we have a root name and suffix, we might be done if the molecule doesn't have anything fancy going on. But frequently, organic molecules have substituents, where plain old hydrogens on a carbon chain can be replaced by other carbon chains or halogen atoms like chlorine, bromine, and iodine, for example. We communicate where substituents are by adding prefixes before the root name. Plus, just like we had to count carbons for alkenes and alkynes, we need to communicate where every substituent has done its substituting. If we're dealing with an alkane where the longest carbon chain only has single bonds, we'll number the chains so that the carbon atoms with the substituents get the lowest numbers. For example, let's take our hexane from before and replace 1 hydrogen on a carbon with a CH3 group. So in this case, we have an alkane, and we want to number the longest 6-carbon chain so that the carbon with the substituent is 2, not 5. Remember, we want to keep the numbers as low as possible. The CH3 group takes the same name as a 1-carbon chain root, meth. And because this group is a substituent, it gets a new ending spelled YL. So the prefix we add is 2-methyl to communicate where and what it is. And this compound is 2-methylhexane. If the molecule is flipped over, we could start from the left and it would still be 2-methylhexane. They're the same compound no matter if the methyl is drawn on the right or the left. If we have 2 or more of the same substituents, we add di, tri, tetra, and so on to the prefix. So if we took 2-methylhexane and added another CH3 group to a different carbon, we get 2,4-dimethylhexane. Notice the punctuation here too. The numbers are separated from each other by a comma and are separated from the words by a dash. But there are other substituents besides carbon chains. Let's say we take our 2,4-dimethylhexane and replace a hydrogen atom on carbon 3 with a halogen like a chlorine atom. So the molecule name gets another prefix. Halogens get the ene in their name replaced with the letter O. So chlorine becomes chloro, bromine becomes bromo, and iodine becomes iodo. That means we need to tack on the prefix 3-chloro here. Lastly, when we add substituent prefixes, IUPAC rules say we need to put them in alphabetical order, and the multipliers di, tri, and tetra do not count when we're alphabetizing. So this molecule is named 3-chloro-2,4-dimethylhexane. These rules about substituent prefixes are mostly the same for alkenes and alkynes, except when it comes to numbering the chains, the double and triple bonds between carbon atoms have priority over substituents sticking out. So we start numbering the chain closest to the bonds instead of the substituent. If we take our alkene friend pent-1-ene and add an ethyl group, that's 2 carbons and 6 hydrogens at carbon 3, we name this 3-ethylpent-1-ene. Or if we put 2 methyl groups on the 2nd and 7th carbons of the alkyne oct-4-ine, meet the spectacular 2,7-dimethyl-oct-4-ine. Now that we have the basics, we can start naming any compound, even if they look kind of complicated with more than one functional group and substituent, like this molecule. But we got this. Don't worry, we have our trusty steps. Number 1, find the longest carbon chain and give it a root name. In this case, we see there's a 7-carbon chain here, so the root is hept. Number 2, identify the highest priority functional group and add its suffix to the root name. Alkenes and alkynes have equal priority when it comes to numbering, but when an alkene and alkyne tie for the lowest number, the alkene wins. We'll count from both ends to see what's up. And look, because the alkene and alkyne tie for the lowest number, the alkene wins. So we'll use the numbering where the double bond is lower. Now we have to name our double and triple bond functional groups. And the alphabetical order rule still applies here. So with the root and suffix combined, we have hept-1-ene 6-ine. Finally, number 3, identify the types of substituents and add a numbered prefix to the root name. In this case, there's a bromine on carbon 4 and a methyl group on carbon 3. Taking alphabetical order into account, we add 4-bromo-3-methyl before the root and suffix. And we've conquered this puzzle! It's 4-bromo-3-methyl-hept-1-ene 6-ine. It's kind of a mouthful to say, but so much more useful to chemists than if I named it Depicting or something. Now, remember that conundrum from the beginning when we asked our lab partner for dichloromethane and got a bottle of methylene chloride? Let's build those molecules. Looking at the name dichloromethane, we know from meth that this is a single carbon and ane that it's an alkane with single bonds. The dichloro tells us that we have 2 chlorine atoms connected to the only carbon, no substituent number required. That's the skeletal structure. And if we want to get all fancy with a Lewis structure, we know that carbon often makes 4 bonds, so we can add 2 hydrogen atoms to finish it off. Methylene chloride is trickier because we can't use our IUPAC rules. We just need to know that methylene is a common name for a CH2 group. Then, because chloride is in the name, we can get to the final structure by filling in the 2 open spots with chlorine. The end structure is the same, so our lab partner did know what they were doing. But calling this compound dichloromethane makes it easier for scientists to know they're talking about the same thing. In this episode, we learned that there are 3 steps to naming molecules, which include the root name, a suffix based on functional groups, and a prefix based on substituents. And we numbered the longest carbon chain by giving the highest priority functional group the lowest possible number, or whatever gives substituents the lowest possible numbers. Next time, we'll learn how to give molecules systematic names when they have functional groups with heteroatoms. Thanks for watching this episode of Crash Course Organic Chemistry.
So, they had approximately 12 minutes of reminders about the IUPAC nomenclature rules, and hopefully if you're watching the video, that will allow you to both use the learner guide and the video that was there from YouTube to review and think about the nomenclature naming rules. And I don't need to go through them again for you, but we have a slide here just in case you want a screenshot rather than the whole video in terms of what our IUPAC nomenclature rules are. Very, very important in naming organic compounds, very important for our Cycle 3 students, and very important for our own revision. So some of the examples that you see in front of you here, you will also find them in the learner guide. Now, let's have a look at a one-pot question. So I'm going to give you about 10 minutes now to see if you can answer the question of how to name these compounds that you see in front of you here. Have a go, use the learner guide, go rewind the video, have a look at the slide if you like, or go through the video point by point and see if you are now able to name these compounds that you see in front of you. I'll be back with you in 10 minutes to check the answers. Okay, so I'm sure you had a good go at this. Let's have a look and see if we can go through the solutions to the questions. Let's start with this one. 2-cyclohexene 1-ol. So, why have we got 2-cyclo? Because the double bonds on the second carbon. Hexene because we've got how many carbons? 6. And 1-ol because that's right, alcohol group is on the first carbon. Then we've got 4-chloro, 3-methyl, heptanol. Excellent. Good going, guys. 3-bromo, 2-phenyl, cyclopentanol. Again, look at where the numbers are. Look at the phenyl group. Look at the bromo group. Which carbon number they are on is in the name that's given. And then the next molecule we've got is 3-butyne 1-ol. So the functional group of the alcohol is found on the first carbon and the double bond on the third. Phenylmethanol or benzyl alcohol. Excellent, well done. Okay, another question for you then. Let's have a look at this. The melting of alcohols in water is high. Why? Why is the melting point of alcohols in water high? Is that a correct statement? Someone correct me. Someone in the group today. The solubility, the melting point of water, of alcohols in water. So the solubility in water is reduced by the rise of the molecular mass. Who can tell us why? Alcohols have a relatively high boiling point when compared to hydrocarbons with the same molar mass. The boiling point of alcohols increases as the molecular mass increases. That's due to the increased strength of interaction between the molecules. The greater the number of hydroxyl groups, the greater the solubility and the greater the boiling point. Alkyl halides. Let's have a look. Think about the nomenclature rules. Refer to your learner guide. Now, if a hydrogen is replaced by a halogen, the compound is an alkyl halide, such as methyl iodide. What about the nomenclature of the alkyl halides? Same naming rules. Let's have a look. Common name of the alkyl group comes first. It's followed by the name of the halogen, and it's expressed as IDE at the end. Ethyl chloride, ethyl fluoride, isopropyl iodide, sec-butyl bromide. So, bromo cyclohexane, cis 1 bromo 9 octadecene. Very long name. Always treat the halogen as a substituent, which means it's added to the beginning of the name. So, 5 minutes. Can you name the molecule? Be back with you in 5. Use your learner guide to see how to apply the IUPAC nomenclature rules. Okay, let's see your answers then. Let's have a look. Okay, so could you name the molecule? How long did it take you, and were you able to use the nomenclature rules in the learner guide? 1,5-dibromo, bromo, 2,4-dimethylpentane. Well done. It's very important for you to go through the rules, both for your own Cycle 3 teaching and your refresher of your Cycle 3 chemistry knowledge. IUPAC rules are very important and definitely help us plan our lessons and activities very well when we're teaching Cycle 3 chemistry. So, ethers and nomenclature. General formula ROR, where that last R is different from the first R, and they can be considered as derivatives of water, where both hydrogens are replaced by organic groups. So remember, your R is referring to an organic group. The bond angle at the oxygen is close to a tetrahedral angle, and you can see the shape just there at the bottom of the slide for you. So what about the nomenclature of the ethers? You put the common name of the alkyl group first, followed by the word ether, such as dimethyl ether or diethyl ether. The IUPAC name, the smaller the alkyl group is converted to an alkoxy name and is used as a substituent. Methoxy, ethoxy, you can see all of these examples here, and it's an important rule for you to remember in the nomenclature of ethers. What about amines? We've got a functional group with a nitrogen atom. The systematic name for an amine is formed by dropping the final E of the alkane and adding the suffix amine. Common names that use the name of the alkyl group followed by the suffix amine are also widely used. So you can have ethanamine or ethylamine, diethylamine. Two good examples for you there. Try seeing if you are able to name any more amines. The general structure. So when we study Cycle 3 chemistry, we know that functional groups affect the bond angles and therefore the chemical properties and physical properties of the chemical compounds that we come across. And amines are classified according to the number of R groups that they have. Remember, R groups are their functional groups, which are directly attached to the nitrogen atom. There we have the examples shown very clearly to you. A primary amine has one R functional group attached to the nitrogen. A secondary amine has two R groups, functional groups, attached to the nitrogen atom. And a tertiary amine has three R groups attached to the nitrogen atom. So, some biomolecules with amine functional groups. Lysine, adenine, epinephrine, cocaine. These are all molecules that you've commonly come across in your chemistry teaching, and you are well aware that they have these amino acid amine functional groups. Amino acid, lysine, adenine. Epinephrine, we know, is adrenaline neurotransmitter, very important in the body. Cocaine, a stimulant, not one that we really talk about with our students, but in fact has a very complex structure, which is a good one to use when you're trying to come up with the IUPAC naming. So reactions of amines. Primary and secondary amines can form hydrogen bonds, therefore they have higher melting points and boiling points than hydrocarbons or alkyl halides. Important rule to remember. Tertiary amines cannot form hydrogen bonds between their molecules because they lack the polar NH bond. Amines of a low molar mass can often be quite smelly, are water-soluble, and weakly basic. Amines also undergo a variety of reactions, including substitution reactions. So let's have a go at this activity now, 20 minutes. Are you able to determine the type of reaction and predict the products for each of the reactions listed there? So guys, we'll meet back in 20 minutes. Let's have a see if you are able to solve these puzzles. Okay, welcome back. Let's have a look at the solutions then and see how we did with these chemistry problems. So in A, the reaction of the hydroxyl group, oxygen and hydrogen, of the sodium hydroxide reaction substitutes for the iodine in the organic reagent. So we get NaI released. Substitution reaction. B is also a substitution reaction. You can see that the functional group is substituted. And C, this is an elimination reaction since the acidic Cr2O72 minus is a strong oxidizing agent. Well done, guys. So we'll have a break there now, and I'll meet you in about 30 minutes. Okay guys, welcome back after that short break. Let's go straight into aromatic hydrocarbons. So you can see some examples of the aromatic hydrocarbons on the screen there in front of you that you may come across in Cycle 3 chemistry. So, benzene is an aromatic hydrocarbon and is a resonance hybrid. Its p-bond electrons are delocalized. Aromatic compounds are usually stable, and although they contain double bonds, they undergo substitution rather than addition reactions. An important thing to remember, substitution rather than addition. The stability of benzene, it releases less energy during hydrogenation than expected because it is already much more stable than a similarly imaginary alkene. Aldehydes and ketones. They both contain the carbonyl group, carbon double bond O. The R indicates the hydrocarbon groups, and aldehydes are named by replacing the final E of the alkane with the suffix al. Ketones have the suffix -one, and the position of the carbonyl must always be indicated. Reactions of aldehydes and ketones. Reduction to alcohol is an example of an addition reaction, as you can see in the example there, where we go from cyclobutanone to cyclobutanol. Organometallic compounds, which have a metal atom covalently bonded to carbon, add to the electron, pour carbon, as you can see in the example. So, example. Are you able to fill in the blanks? Take 5 minutes and see if you can manage to do that. So, here's your solution. Substitution, oxidation, elimination, addition. Carboxylic acids and esters. Carboxylic acids. Carboxylic acids contain the functional group COOH, depicted as shown. Carboxylic acids are named by replacing the E of the alkane with the suffix oic acid. Carboxylic acids are weak acids in water and react with strong bases, as you can see in the example. Here's some examples of molecules with a carboxylic acid functional group: methanoic acid, butanoic acid, benzoic acid, octadecanoic acid, also known as stearic acid. Esters. The ester group is formed by the reaction of an alcohol and a carboxylic acid. Esterification is a dehydration condensation reaction. Ester groups occur commonly in lipids, which are formed by the esterification of fatty acids. Can you predict the reactions of the carboxylic acid family? Take 15 minutes and see how you do. So let's have a look and see if we can solve these predictions for the reaction of the carboxylic acid family. Give yourselves 20 minutes and see if you are able to solve these problems. Predict the products of the following reactions. Okay, so welcome back after your 15 minutes of problem solving. Let's have a look. Check your answers. Did you have water as a product? Did you get the right product reaction with the correct functional group? Again, check your answers. Did you get the correct structural formula and the correct products? Okay, well done. You've got through day 2 of the Chemistry Foundations subject knowledge training. We looked at the classification of hydrocarbons, we reviewed alcohols and alkyl halides, we reviewed ethers and amines, and we looked at aromatic and carbonyl compounds. I hope this information has helped you review your Cycle 3 chemistry knowledge in these areas, and we look forward to you joining us for more training in the future.